Hello, novice statisticians. How are you doing? I am so excited because today we start a new unit going beyond means. And I'm very excited to be talking with you about correlations today. I am broadcasting from sunny Atlanta, Georgia, and let's just jump right into it. Okay, I'm on 9A, correlation. Okay, slide 2. So you get scores on two variables for each individual, right? And a correlation coefficient is calculated using the two variables. Let's say they're X and Y. Okay, and we're testing the relationship between X and Y across all the people in our sample. Okay, or whatever it is that is our unit of analysis. Slide 3. There we go. So let's say we have Jack, Jill, Dave, and so on are people. Questions that are not addressed by correlations: are Jack and Jill's scores different? Okay. Right? We're not doing those kind of questions. Are Jack's scores typical for most people? Are males and females or any other group scores different? Okay. You know how to test if two scores are different, right? You use a what? A what? Yes, a t-test. Okay. We're only looking at whether X and Y tend to vary together in general across everyone in our sample. So here are some questions that we can use a correlation to address. For example, do children learn more from discovery learning or guided instruction? There will be for that question we'll be correlating the learning, however we measure it, with the type of instruction. Now, the nice thing about the word correlate is it's one of the few words that's the same in English as it is in statisticalese. Okay, so your understanding of the word correlate, you can use it in this case. All right. Is the amount of red meat I eat related to my risk of getting cancer? Do males tend to score higher on math tests than females? Now, I said we weren't looking at differences, but we could correlate high scores with gender, right? Does life expectancy for countries vary as a function of per capita consumption of alcohol? Right? And so there a unit of analysis would be country, right? And we're correlating the consumption of alcohol and life expectancy. Do vegetarians have less heart disease than those who eat meat? And that, of course, that question is related to question 2. So those are some of the kinds of things we can look at. We're correlating two things together. Does meat correlate with heart disease? Okay. Or does meat correlate with cancer? You know, that kind of thing. All right, so what we're going to do in this lesson is we're going to look at correlation in many different ways. So first, let's look graphically. Okay, so imagine you have some points graphed in space on graph paper, right? And they're kind of, you know, spread out, like this picture that I have on the slide here. The green line, and so we have our x-axis and our y-axis, right? So the green line, you know, it's coming down, it's hitting the x-axis. That represents the mean of x. And that purple line going across, hitting the y-axis, represents the mean of y. Okay, and then the dashed line represents a trend or regression line, and we're going to be talking a lot about regression next time. But for now, just think of it, it's the line that's, you know, kind of in where everything kind of lines up. You know, it's like It's an estimate of where, the dots kind of fall, right? But in line form. Okay. Data point A. See where I circled one of those points and wrote an A? That is below the mean of X, right? I'm going to try to do this in a way that makes sense for the video. Below the mean of X and below the mean of Y. And data point B is above the mean of X, right? And above the mean of Y. See that? So A is below the mean of X and below the mean of Y, and B is above the mean of X and above the mean of Y. And all the points are kind of near the trend line, okay? X and Y vary or change together. They are strongly correlated, okay? And you can try different correlations after you, if you follow that link, you can try different correlations after you watch the videos of our lesson, okay? And that's where I got that graphic from. It also shows the shared variance. In this case, they vary together by about 64%. And I'm going to talk more about variance in just a moment. Okay, so slide 6. Here's another look at correlation graphically. Okay? It's like the scattering of the points, right? So a perfect positive correlation, you're going up the mountain, okay, up the mountain, versus negative correlation goes down the mountain, okay? And so a perfect correlation is all the points are going in the same direction, right? A high positive correlation is most of the points are going the same way, right? Low positive correlation, you get more scatter. No correlation, they're spread out, okay? Just because one is high doesn't mean the other is high. Just because one is low doesn't mean the other tends to be low. They're all spread out, okay? Low negative correlation, going down the mountain, and they're kind of spread out, but you can see a trend there. High negative correlation, they're clumped closer together, and then a perfect negative correlation, they're lined straight up, okay? And we've graphed X data and Y. X data and Y. Okay, so 2 variables. All right, so that was graphically. Now let's talk about variance. Okay, remember when we learned the formula of variance long ago, and it was on a blue slide like this? You learned about it way back near the beginning of the course. And we measure how each data point varies from the mean by calculating the deviation, right, or difference, squaring them, right? Summing the square deviations, right? Adding up all those square deviations and dividing them by the sample size adjusted. But what if we have 2 variables? Okay. What if we want to know whether the data points tend to vary from their means in similar ways? Like we were talking about point A and point B. They were both above when one was above the mean, the other one was above the mean. And one below the mean, other below the mean. If we have 2 variables, do the data points tend to vary from their means in similar ways? Okay, so covariance algebraically. So we know that for variance, it's some data point X minus the mean of X times squared, right? So that's times. And so we got X minus the mean of X times X minus the mean of X, right? That's what squaring does. But if we have 2 points and we sum that and then we divide by n minus 1. Now, if we have 2 points, right, we have an x-axis and a y-axis now, right? So we can do X minus the mean of X times Y minus the mean of Y. We sum all the products together. So we're doing that for each point in our data set, each person. We got Jack's X minus the mean of X. times Jack's y minus the mean of y plus Jill's x minus the mean of x times Jill's y minus the mean of y plus, and so on, divided by n minus 1. And that's what covariance is. So you know what variance is, and now you know what covariance is. And basically, covariance is a statistic representing the degree to which two variables vary together. Okay, slide 9. So remember, like, a positive times a positive equals a positive, and a negative times a negative equals a positive, and a positive times a negative equals a negative, and a negative times a positive equals a negative. Remember that from way, 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 way back. Okay. So when you have a pattern, when x is higher than its mean, and so is y, x minus x bar, or that point that was above x, above the mean of x, right? Or it would be over to the side, the mean of x, right? When that's positive and the y is above the mean of y, okay, so that your data point, Jack's score, is above the mean, right, for y. When both of them are positive together, you're going to get a positive covariance. When both of them are negative together, okay, you're going to get a positive covariance. When they differ, if one is high, that means the other is low, you're going to get a negative covariance, and vice versa. When x tends to be low, y tends to be high, then you'll also get a negative covariance, okay? Where you get no varying together is when there's not a pattern, okay? When knowing that x is above the mean doesn't necessarily lead you to believe that y is going to be above the mean, okay? When there isn't a pattern, the deviants tend to cancel each other out, right? The deviations tend to cancel each other out. And you're adding them together. You're adding the products together. And yeah, you get some that are positive, some that are negative, and you end up with a number close to 0, okay, for the covariance. Now, the problem with covariance, slide 10. The problem with covariance is that it's not standardized, okay? It really depends on what your units are. And there's not a way to compare, one covariance to another. You can't really compare the two numbers because it all depends on the units that you're using. Okay, so this is where Karl Pearson comes in. He's known as like the father of modern statistics because in the 1890s, he invented the most popular correlation statistic. Now, what's a correlation? To standardize the effect size D, for example, remember, we divide the effects, such as the pre-post difference, right, by a standard deviation. Usually for pre-post, we divide by the standard deviation of the pre, right, the pre-test scores. To standardize the covariance, we divide it by the product of the standard deviation of x and the standard deviation of y. Okay, so then we get, we get a way of looking at these numbers that standardize across units. Okay, and now Karl Pearson invented this idea, okay, this correlation coefficient where you're getting a standardized covariance. In the 1890s, he was working with a professor named Weldon, who was a zoologist, and he was exploring the properties of the normal distribution and correlation in a study of shrimp. He was looking at like shrimp organ size, which organs correspond with each other, tend to vary together. And there's been a lot, of interplay between biology and genetics in particular, and statistics, and you see that in history. So Karl Pearson, he, was working with this biologist, Statisticians and, applications go well together, right? Just like statistics and education. All right, go well together. And he came up with this coefficient. Okay, slide 11. So R, Pearson, why it's called R, I'm not sure because the R is kind of in the middle of his name. Maybe P was taken. R equals the covariance of X and Y, which we had the formula for that before, right? It's like the variance, but you have X and Y, and then divided by the standard deviation of X and the standard deviation of Y. And that gives us a standard scale with values ranging from -1 to +1, regardless of the original units. It can be used for interval or ratio data. It can also be used with other kinds of data. We just call it something else. Okay, and in your textbook, it's instead of for an ordinal scale, instead of saying Spearman's rho, it says RS. So like Pearson's R, but it's Spearman's. Yes, all these different people inventing different ways of finding a correlation. But Pearson is credited with his product moment correlation coefficient. Okay, so slide 12. Let's look at an example. Okay, ice cream sales. A student group sells ice cream each day at the end of a summer camp as a fundraiser. Do sales vary based on the weather? Okay, let's see. And when the temperature was 14.2 degrees Celsius, they had $215 worth of sales. When the temperature, I'm going way down here, was 22.6 degrees Celsius, they had ice cream sales of 445. So just an eyeball look at this tells me that it looks like maybe when the temperature was lower, they sold less ice cream, and when it was higher, they sold more. How would we figure this out? Well, we could do it algebraically, right? We can calculate the covariance by subtracting each temperature minus the mean of temperature and subtracting the dollar sales minus the mean of the sales. Okay, and so we're getting our two deviations there, right? And then we multiply those two columns together, right? And then we add all of our products together. That's that summation sign. We add all the products together, and then we divide by n-1 to get the covariance, right? And the n, I think in this case, is 12. So when column 2 and column 4 are both large with the same sign, our product of those two columns is going to be large and positive. When they're both large, when 2 and 4 are both large, but they have opposite signs, our column, right, all the way over to it's going to be this side on you. When we multiply those two together, the product of our two deviations is going to be large and negative. Okay. All right. So if we go through those steps, we get the covariance equals 484.09. And you can check your answer. There's a covariance formula that you can use in Excel. Okay, now correlation. All we have to do is divide that covariance by the product of the two standard deviations. Okay, so that R, Pearson's R, would equal 484.09 divided by the product of 4.01 and 126.04, which equals 0.96. Now, remember, correlation varies from 1 down to -1, and 0.96 is very close to 1. So we would say that that's highly correlated. And in Excel, it's Correl and with your the range of cells in the parentheses. Almost all of the variability in these variables is shared. they tend to almost always perfectly vary together. So you interpret it. If it's near 1, it means that someone with a high score on one variable is very likely to have a high score on the other variable. You're going to hear this again and again throughout this presentation. If it's near -1, someone with a high score on one variable is very likely to have a low score on the other variable. If it's near 0, it means that the score on one variable doesn't tell you anything about the score on what the score on the other variable will be. So let's look at slide 17. IQ and GPA. You would expect a high positive correlation, right? So they would be clustered close to a trend. Clustered close to the trend if you were to graph those two variables together with a scatter plot. Correlation between IQ and weight? None. That shows that our statistic is 0.13, right? Which suggests that there's a slight tendency of people who are a little heavier to have a slightly higher IQ. So, woohoo! Okay, and let's see. Let's go to slide 19. Correlation between IQ and errors on an exam. We would expect those to be negatively correlated. We're going down the mountain, okay? The higher the IQ, the lower the errors. Okay, so now there are some things to look out for. 1, if the range is restricted, if you looked at if the data could possibly go further out, but for some reason you're looking at you're only looking at a certain portion of it. So for example, shoe size and height tend to be correlated, right? So that graph, the first graph shows, a full range of shoe sizes from 4 to 12. And then heights along the y-axis, right? And so you can see that there R is 0.71. This next graph only shows, women with shoe size 8 and 9. Okay, so we've restricted the range of what we're looking for, and the correlation is only 0.16. Another thing that can happen is when you have a score that can't go any higher. An example of that is GPA can only go up to 4, right? And so then you tend to get a lot of people clustered at the top. And so if you look at one part of the graph, let's say we're looking at time studying and seeing the correlation with GPA. Looking at one part of the graph, the more you study, the higher the GPA, but you can't go higher than 4. So there are a bunch of people over here. And if you look at just that part of the graph, you don't get a correlation, okay? Because the range is restricted. That's called a ceiling effect, when you can't go as high as you might need to in order to measure everyone accurately. Okay, slide 21. Another thing to look out for is nonlinearity. There is a relationship between performance and anxiety, but Pearson's correlation coefficient is based on the assumption of a linear relationship, as in straight line, not a curvilinear relationship. So the relationship between performance and anxiety is that a moderate amount is best. Low anxiety when you don't care is not good, and very high anxiety when you're freaking out is also not good. So I hope that all of you have just a moderate amount of anxiety about statistics, because that means your performance is going to be super high. Okay, so the best fitting straight line would not match the data points very well, and the correlation would be low, even though there's clearly a relationship. Slide 22. When you have subsamples that are not the same population, that are heterogeneous, right? You could get what looks like a strong correlation if your two groups are together. For example, the relationship between height and weight for males and females combined is an example that's in your textbook, right? And it looks like, hey, there's a certain correlation there. But when you analyze females and males separately, it's very different. Okay, the correlations they get are very different. So that something to think about. Another thing is that extreme observations will give you can really affect your correlation coefficient. Okay, because remember we're doing the distance between a particular point and the mean, and then we're multiplying that distance or that deviation with another number. You know what I mean? And we're adding. So if there's an extreme observation, if there's a mistake, if you did a typo, like if you wrote the temperature as 142 instead of 14.2, the correlation changes from 0.96 to minus 0.38. Okay, and the trend line that you would see, taking into account that point, would be flatter and go like this and even. So the right thing to do is, if there's an extreme observation, you can tell your reader what the correlation is, both with and without that extreme observation, particularly if you have a sense of why that extreme point might have happened. So if that was an anomalous school or anomalous class, or a student who had a particularly unique situation, that kind of thing. Okay, and so that is it for part A. And so I look forward to seeing you soon for part B. Okay, see you soon. Bye-bye.